In this module, we're going to talk about the interstellar medium and the birth of stars. Let's start first with the interstellar medium. In space, there is almost nothing there. Almost nothing. In interstellar space, which is the space between stars, there's about 1 atom per cubic centimeter. So by contrast, Earth's atmospheres, there's 10 to 20 atoms per cubic centimeter, and the best vacuum Earth that we can produce is about 1,000 atoms per cubic centimeter. So while space is not empty, completely empty, is as empty as you could possibly imagine. There's also dust grains in interstellar space, but dust grains are far more diffuse. There's maybe about 1 grain per cubic kilometer. So basically, distances between grains is about a kilometer or so. Gas in the ISM basically are in 3 different phases, right? In the ISM being interstellar medium. There's the cold phase. Cold phase is pretty cold. It basically goes from about 10 degrees Kelvin, absolute zero is 0 degrees Kelvin again, right, to about 100 degrees Kelvin or so. Then it's the warm phase, about 8,000 degrees Kelvin, and then the hot phase, but above a million Kelvin. Most of the volume in the gas is hot. Most of the volume is hot. So by volume, most of the gas is hot. By yeah, so most of the volume is made of hot gas, but by mass, most of the gas is warm or cold. So the cold gas is especially important because they are the clouds that ultimately form stars. And so these are the birthplaces or nurseries of stars. So some of these cold clouds have stars in them, right, that they have formed. And the heat of the gas be hot enough to have some ionized hydrogen around them called H2 regions. That's the Roman numeral 2, not II. Clouds cool enough to have the hydrogen in the form of atoms, or in the coldest cloud, for instance, molecules of hydrogen, are called H1 regions. So hot clouds are bright, and the light they emit can be seen. Right. So most cool clouds emit little visible light and are observed as dark nebula. Dark clouds block the light from the stars behind them, basically because the dark clouds, which are cool, also form quite a bit of dust. So dust scatters light that's shorter than the size of the typical dust grain, um, uh, uh, and reddens the light that goes through. So dust grains are typically nearly the size of the wavelength of light. And so basically, if it's much smaller, then what happens is that the wavelength of light can pass through it more easily. All right, so that what ends up happening is it preferably ends up scattering the bluer light, leaving the redder light behind. So for instance, you can see this picture here, right? There's some reddening at the edges and stuff, but if you look at the infrared, you'll see right through that dust cloud, right? So these cold clouds are cold enough to have a lot of dust. The dust grain is about hundreds of nanometers in size, which is about the wavelength of visible light. And so because they're such a size, they affect different colors differently. So you, a person, is much larger than 100 nanometers. So basically, if I hit you with blue light or red light, it's the same thing happens, right? You absorb the light, right? But the dust grain, because they're roughly the same size as visible light, they can scatter some wavelengths more preferentially to others, usually bluer wavelengths. So this is reddening due to Barnard 68. You can see at the edge of the cloud, basically as it gets to deeper and deeper, the stars go from basically white to redder and redder, right? Kind of like sunsets, right? And the deepest part of it, basically the dust is thick enough that actually scatters all the light out or absorbs all the light and then you can't see anything. If you look at infrared, which is much longer wavelength, then the dust doesn't scatter as easily. You see all the stars right through it. You still see reddening though, right, as a result. The same effect is also responsible for sunsets, basically. Sunsets, the sun is low in the sky, passes through more of the Earth's atmosphere. More of the blue light gets scattered out of the line of sight. And so as a result, what we see is basically we see the brilliant reds of a sunless set. All right. So in a nebula, all right, you will see basically different kinds of light, right? So for instance, if you have light from um, a star, for instance, right? Then basically what happens is that you get basically emitted red light, right? And if you see some starlight that gets scattered off a dusty cloud, then that preferably scatters blue light, and so you get scattered blue light. So this light is actually scattered light, and this light is basically the red lights, where it's basically uh, there's a lot of absorption. All the blue light is scattered out of the line of sight, and here you scatter the light into our line of sight, right? So this is very similar to basically why the sky is blue, right? So this is the sunset. You're looking through toward the sun through a large amount of atmosphere, so it looks red. And this is why the sky is blue, right? You're not looking toward the sun, we're looking at the sky. We know the sky is blue, but you're seeing the scattered blue light from the sun through the sky. So here's the scattered blue light from basically a dusty cloud. So this is scattered blue light, unscattered red light. Right. So the reflection nebula is blue for the same reason sky is blue, right? So you look white light, you look directly at the sun, right? And if you look basically off the line of sight, what happens is that light, which is causing sunset somewhere else, that's light from the sun, which is causing sunset somewhere else, that blue light is scattered into our line of sight, and so we notice the sky is blue then, right? So reflection nebula is blue for the same reasons the sky is blue, right? This is the Eagle Nebula, right? These pillars are molecular clouds, and within these pillars are the nurseries that hide newborn protostars, right? So you see some streaming light that comes out of this thing. There are stars behind them. In some cases, the stars have heated up enough gas and dust around to emerge out of their cocoon, and see young protostars that are basically being born, right? So you see the light being basically emitted from the system, right? There's the Rosé Nebula, right? It's also very cool. You'll notice in the center there's a big hole. Look at the closely at the hole. What is it? These are blue stars, right? So these stars are really young. They've just been formed within the Rosé Nebula, and they're emitting so much radiation and giving us so much powerful winds that they're blowing a hole in it. So this is a hole basically that's blown out, right, by these blue stars in the center, and a bunch of blue stars away from it. So the pressure of this of these blue stars, right, from the starlight blows gas away from the center. These clouds also give off radiation in the radio, it turns out. And these come in basically two different ways. One is radiomolecular lines, all right? So these are similar to spectral lines of atoms, except they're formed by molecules, and molecules have lower energies typically than atoms, and so basically give off the energy in the radio. So this is radio emission. And also there's 21 centimeter radiation from hydrogen that's not due. So last time when we talked about spectral lines from hydrogen, that's due to changes in the orbit. This is due to flipping of the electron spin, right? Because the hydrogen atom has a hydrogen nucleus has a natural magnetic moment associated with it, right? So this leads to 21 centimeter emission, and this is indicative of atomic hydrogen. So gas radio emission from either molecular lines or 21 centimeter radiation from 21 centimeter radio emission from hydrogen allows you to map the gas while looking directly at emission from stars. Okay, so these are some molecular lines. One of the most common molecular lines is carbon monoxide. Partially the reason why it's important is carbon monoxide is fairly easy to form because in terms of material out there, carbon and oxygen are two of the most common materials after hydrogen and helium. So you can form that readily. And it also turns out to be a strong radio emitter as well. So basically this is a carbon monoxide emission, right? Or 21 centimeter emission. This is a galaxy, and you see basically we're strong in carbon in 21 centimeter or hydrogen emission. It basically follows along the spiral arms of these galaxies, right? So you see it in 21 centimeter and also in infrared radiation as well. So if we map the gas in carbon monoxide, CO, which is a molecule, and atomic hydrogen, H1, right, with the 21 centimeter emission, we know that molecular clouds contain enormous amount of gas, right? Typically contain up to about a million times the mass of the sun, right? These clouds are also basically in enormous collection known as molecular cloud complexes, right? So this is basically a number of molecular clouds which are not forming, but are associated closely just because they're essentially forming from one big stream, right? So these are molecular cloud complexes, and they form stars in the densest parts of these molecular clouds. So star formation is the process of converting clouds of gas and dust to collapse and form a star. This is a pretty simple idea, but we still don't understand it quite well, right? In principle, we could break it into 7 stages, but we could think about it as one continuous stage, right? So the first thing is that we collapse all the molecular gas and form the stars, right? So in stage one, the molecular cloud begins to collapse. Usually we see this in molecular lines, right? So we start with a fragment of a molecular cloud, right? So this is the Rosé molecular cloud, right? And basically you can see some of the denser regions right here, right? So these are very strong emission in molecular lines, right? And then the cloud, as it basically collapses, it collapses into filaments, which are tiny little pieces, and these pieces fragment into tinier, even tinier core, which are very dense objects, which basically eat up all that eat up some of the gas. So I'm going to zoom in here in a second. Well, maybe not. Right. So so now we're going to zoom in, and you can see there's a region here which is particularly dense that forms a core. And guess what? It's starting to form, that core is starting to eat up all the gas and start to form the first protostars. And these cores, because of gravity, start to attract each other as well, and they form yet more and more protostars as they collapse. Okay, so initially these cores are cold as they collapse, right? Because they emit infrared radiation, the radiation allows them to cool. But as they get denser and denser, the radiation has a harder and harder time trying to escape, and eventually start to heat up. So at this point, when they start to heat up, a protostar is born. So here's a protostar. Star is still forming, it's still getting gas from the environment, but it already has a hot central thing that will eventually be the star, right? And they're typically surrounded by disks of gas and dust. In this case, that has a powerful jet being emitted from it. This why this is an artist's conception. A lot of these objects show very powerful jets. All right, so there's a protostar. This is Orion. There's a protostar in the center. This is the disk of gas and dust that surrounds it. So you basically see it in the plane, right? So there are various examples of these protostars. So these are basically I think this is Orion, but I guess these are some protostars from the Trapezium Nebula. Right. Okay, so because they're star light, okay, they will have a temperature and a luminosity. You could put them on the HR diagram or Hertzsprung-Russell diagram, but notice they're can be much brighter and cooler than the sun. So that's the sun right there. This is brighter. This is cooler. And there's the our protostar right there. So it's typically much larger, typically about 100 solar radii, much brighter than the sun, but also much cooler, right? And as they evolve, so these things actually do move, they will eventually collapse and join up on the main sequence. So if this thing ultimately will be a one solar mass star, it will form and join up on the main sequence at where the one solar mass stars sit, right? So as the protostar contracts, it heats up, but also gets dimmer, and that's because the star is getting smaller because it's contracting. And during this phase, a lot of them give off jets of gas. These are what called Herbig-Haro objects, right? So eventually nuclear fusion starts up and the protostar transitions from being a protostar to an actual real star and sits in the main sequence. All right. The fact that the star, as it cools off, so these stars are cooling off because they're releasing radiation and contracting. All right. Um, but as they cool off, they actually heat up. This is an example of what's called negative heat capacity. So most things have positive heat capacity. So that means as you heat them up, they get hotter. As you cool them down, they get cooler. But this is opposite for stars and protostars in general. It's a subtle effect basically because of nature of gravity. As you heat them up, it gets cooler. As you cool it down, it gets hotter. So a protostar is actually in fact cooling down because of radiant energy away, but yet it's getting hotter, right? This is a nice idea because it helps you understand a lot about stars if you understand this concept. So here's some protostar evolution. These are HH, Herbig-Haro objects, or HH Herbig-Haro objects, and you see these powerful jets, from these protostars, right? And the disk material that surrounds them. Finally, at the last stage, basically a star is born. So it starts once the star starts fusing hydrogen into helium, so it starts hydrogen nuclear burning, the collapse halts and it reaches what's called the zero age main sequence or the main sequence. Right. So basically that's the main sequence. It starts as a cool molecular gas. It basically forms a protostar at this point. The protostar starts to cool. As it cools, it basically heats up, rising in temperature and dropping in luminosity until it joins up the main sequence and basically becomes a main sequence star. Okay. Once I land on the main sequence, I'm stuck there because that's given by the mass of the star. All right. And it will stay there for its lifetime until they get off, right? And that we're going to talk about next when we talk about stellar evolution. All right. Some stars, however, are not mass enough to burn hydrogen. So these are called failed stars or brown dwarfs, and they range up from the size of Jupiter up to about 80 times the size of Jupiter. Beyond 80 times the size of Jupiter, they actually can fuse hydrogen into helium, and so they're no longer failed stars, they're actually real stars, albeit very dim stars. It also turns out that because stars form in molecular clouds, and molecular clouds typically have about a million solar masses and gas in them, that when stars form, they form in groups, and these groups are called star clusters. So most of these stars are in what's called open clusters, with typically about hundreds to 10,000 members. So basically, it's an example of the open cluster or the Pleiades. You see that in summer sky, Hyades, and the H and Lambda Chi Persei. Right. Um, more extended versions of these open clusters are called associations, right? Um, and so these stars form in clusters because they came from the original break of a single cloud, right? So we see these newborn clusters basically in these molecular clouds. There are several major types of clusters. We talk about open clusters already, and we talk about stellar associations. The difference between them is that open clusters may have thousands of stars. They have some gravitational binding. Stellar associations are much less massive. They're not gravitationally bound and typically extend. So these are clusters in the process of basically being dissolved. Right. And finally, there's one more cluster, which is called globular cluster. These are typically very old. They're extremely massive. Typically, millions of stars sit in them, and pretty compact, about 1 to 10 parsecs, about 3 to 30 light years across. Right. And they are gravitational bound. So if you have massive stars in your star cluster, right? So the stars, when they form the cloud, they form a cluster, and once you form a cluster, you can form some massive clouds, massive stars, and these massive stars give off a lot of radiation, and that radiation tends to break up the molecules, and they have powerful winds to generally blow apart the cloud. Right, and so that's actually what ends up stopping the star formation in these nebulae, because once you form a few massive guys, they basically dominate the neighborhood and they make it impossible for new stars to form. So, for instance, in the Carina Nebula, there's a star or maybe pair of star in the center called Eta Carina, which is some of the most powerful and massive stars in the galaxy, and this Eta Carina is in the process of essentially stopping star formation in the Carina Nebula. Most of these clusters, once they lose their gas from the original clouds, they start to dissolve. And why is that? Well, first of all, they lose a lot of gas. So gas is basically where most of the mass was, which means a lot less gravity. So stars start to drift apart. The galaxy also has its own gravity, and the galaxy's gravity is also pulls apart star clusters. And only the biggest star clusters can stay together, and these are the so-called globular clusters. So they tend to be big and old. Right? And that's it for today.